Hey everybody. So today we're going to analyze some game shows. Today's video lesson is not so much a lesson, but some examples to go through where the idea is I kind of set up the problem and give you guys some time at home to like pause the video, try the problem at home, and then unpause it, and then I go over the solution with you, which I've already pre-done. Because some of these questions the calculations take a few minutes, and it's just not a good use of time to watch for me just to spend 5 minutes punching in on the calculator. We're going to start by analyzing PLINKO in a bit further depth, because we have shown that if you want to have the best chance of getting $10,000, like with one chip, we showed it in the middle slot. However, this doesn't necessarily mean that it maximizes the expected amount of money. For example, maybe dropping in another slot, even though it decreases your chance of getting 10,000, maybe it greatly increases your chance of getting 1,000. And maybe in the expected value calculation, maybe that higher probability with 1,000 makes up for the loss of probability in the 10,000. We just don't know until we actually do it. So we're going to go back to our 4 PLINKO chip positions and create some distributions, and then some expected values. So it's nothing really crazy new. It isn't really new, just applying the things we did yesterday, just having a bit of fun. So here's the first scenario. So dropping in slot A, we don't need to redo Pascal's method. I've already done that for you and displayed the results for you there. So what we did earlier to find probabilities was we added up the total number of ways to reach the bottom. And here it is 2,000. Just get my pen tool here. The total is 2,508 ways to reach the bottom. So the probability of getting 0, for example, well, there's 2 spots to get it. You can get it 483 ways here or 66 ways there, 483 plus 66. So there is 549 ways to reach the bottom and get 0 out of 2,508 ways to reach the bottom. And as a probability to 4 decimal places, that's 0.2189. That is approximately. For the 100, there's actually just one 100 slot. It's 297 out of 2,508. And that gives you, this is the last one I'll do with you guys, divided by 2,508, 0.1184. So you get the idea. I'd like you guys to try the 500, the 1,000, the 10,000. Afterwards, try doing an expected value calculation. How much can you expect to earn on one PLINKO chip in these cases? Well, remember, to get expected value, we take the outcomes, so say 0 times the probability of it happening, 0.2189, and then outcome of 100 times its probability. And you guys will do that for the other three outcomes, 500, 1,000, 10,000, and let's see what you get. So if you want to pause the video now, give that a try. You can unpause and let's check our answer. So I finished off for slot A, and when I finished off my calculation, I did it wrong the first time, but I got about $1,319.69. Now I made a point there. This is using rounded figures, so these decimal values were not exact. What I'd like you guys to do now is repeat this process here for slot B. Find a total, find those probabilities, calculate an expected value. This time for slot B. You have all the work there as far as Pascal method goes. So this would be a good time to pause the video, try slot B in its entirety using decimals, and you can unpause when you're ready. And let's have a look at the results for slot B. All right, so here we go. So there was 3,498 ways to reach the bottom. and I've done all my work in the table, got the probability distribution. Again, I used decimals, so a little bit of rounding. If you added those decimals up, they might not give you 1. You might get like 0.9998 or 9, like, because there's rounding. But if it adds to close to 1, you're in pretty good shape. And I did my expected value calculation at the bottom there, so you can see that I just again applied our formula. Expected value is the sum of all the outcomes times their probabilities. So I just did that, and I actually got that in slot B. You actually do better in slot B per chip, $1,807.99. So not only is slot B actually better to get $10,000, it's just better overall. Makes you more money compared to just over $1,300 for slot A. For slot C and D, I'd like you guys to, we're going to do, save ourselves a tiny bit of work here. So I'm going to do for slot D, I'm going to go through the first little bit of work with you and show you how we can save off a bit of time and make sure our answer is a little bit more precise with no rounding. We do need to get the total here, though. Add up all those numbers in the bottom. 495, 220 plus 77. So for this one, the total is 3,936. Number of ways to get 0, 924 plus 495. That's 1,419. But in this case, I'd like you guys just to leave it as that. No need to do the decimals for this one. Let's leave things exact and see how it goes. For the 100 slot, 154 plus 11, that's 165 out of 3936. I'm going to let you guys do the final 3. And then the reason this could be a shortcut and it gives you a more exact answer is that because all these probabilities are out of 3,396, we can use our shortcut where we do 0 times 1,419, and then that's divided by 3,396 plus 100 times 165, again out of 3,936, and then you guys can do the other 2 on top there. And that, in my opinion, just saves on the calculation side a bit less time, and there's no rounding involved. It gives you an exact answer, whereas the previous few did have some, we did do some rounding. So at this point, if you want to pause, try 500,000, 10,000, try the expected value calculation, and let's see how we do in slot C. Here we go. When I finished off my calculation, I got $2,342.99. So again, we've improved the chance of getting $10,000, but you can see it's just actually a better slot to drop in because on average, each chip is going to make you over $2,300, where for slot B, each chip only got you about $1,800. So definitely better to drop in the middle. Now we want to see if slot D is indeed the best. So you guys are going to do slot D. I'd like you guys to, just as we did here, keep things exact. It's just going to save you work. So keep things exact. Careful finding your total. Get those probabilities as fractions. Maybe even just make sure they add up to 1. Make sure you did it right. And then try the expected value calculation, just like we did with slot C. So pause the video, give this question a try, and then check in when you're done. Here we go. So I've got slot D done here. There was 4,044 ways to reach the bottom. I just have my final answer there for the expected value per throw. So I did do 100 times 1,584 plus 100 times 108, et cetera, up to 10,000 times 924, and then divided that total by 4,044. And I got $2,586.50 per throw. So we can actually reach a conclusion now. Not only did slot D give us the best chance of $10,000, we saw that in the PLINKO assignment, it actually has the highest expected value per throw, beating out slot C by, it looks like, a couple $100. So after analyzing the expected value of all the single chips, would we still drop in slot D? Absolutely, we would. It just makes you more money overall. It doesn't just give you the best chance of 10,000. It gives you the most money per chip. So we've now analyzed PLINKO in complete detail. Anybody that's not dropping their chip in slot D is not playing the game correctly. All right, let's go on to another game. So hopefully you guys have all seen Wheel of Fortune, but Wheel of Fortune, they contestants have to like guess a phrase or a title or something by filling in letters. So they spin the wheel, they land on, let's say they land on 300 and they guess T, and there's 2 T's. Well, then they make 2 times 300, they make $600. And if they guess the puzzle correctly, they get to keep all the money that they earn by spinning the wheel. But one thing if you're producing the show, you'd want to know is, well, how much can I expect to give away during a single show? Like, you'd want to budget appropriately, right? You wouldn't want to have a wheel that gave out too much money, because you want to make money as a producer. Like, that's the ultimate goal. But you don't want it to be giving out too less as well. So it's somebody's job to know how much you could expect to give out every time somebody spins the wheel. So I'm just going to move my face up there. So this is a wheel. It's not a current wheel. Every year the wheel gets more complicated. Back when I was a kid, there was no fancy 5,000 like mini slots there, and there was no like secret prizes. But there is still lose a turn. There is still bankrupt. Lose a turn, you don't lose your money. It just you lost your turn is done. If you get bankrupt, you actually lose all your money. So to keep things simple there, we're going to assume if you land on bankrupt that we're just going to count that as $0 just for the sake of making this a bit easier. So what we're going to do is we need to create a distribution. So we need, for each of these dollar values, we need to find the probability of winning that amount, and then we can do an expected value calculation. So I'm going to make a suggestion to you and help you get started as well, and then let you guys finish it off, and we'll compare when you're done. So there are a lot of possible outcomes. Where is my cursor? There it is. So I'm just gonna, off to the side, gonna get a distribution table set up, just do a rough one. And the lowest value you can get is 200, and you can get 250, 300, 350, 400. I'm going to help you guys out quite a bit getting this one going. You can get 450, you can get 500. I believe there's a 550 on there when I did this one earlier. Yes, there is. 550 and 600. I'm right out of space. I'm going to actually just continue my table to the right. So this isn't 2 separate tables. It's the same table, just extending. And then from there, you can just get multiples of 100. There's no 651. So 700, 800, 900. You can win 1,500. You can win 5,000, or you can get 0. So I'm going to help you guys out. If you look at the wheel and just carefully, maybe if you start at the top with the bankrupt. If you start at the top and count all the different segments of that size going around the wheel, there is 24 of them. So that will help you with the probabilities. So for example, how that helps you is for 200, if you look around the wheel and find out how many 200s there is only one $200 slot. So the probability of getting 200 would just be then 1 out of 24. Pretty simple. 250, there's one slot, 24. For 300 though, if you look around the wheel, there's 2 of the 24 slots that are 300. So if you guys just do a careful analysis, you should be able to get the probabilities up to 1,500 pretty easily. And then we just have to be careful for and those can all be at a 24 to keep things simple. For the 5,000 and 0, just have to be a bit more careful. So 5,000 is actually a third of a 24th. One of those 24 segments, the 5,000 is between the bankrupt. It's just a third. So a third of 1/24th. If you do 1/3 times 1/24th, that's 1/72. There's a 1 in 72 chance of getting the $5,000. And for getting 0, you have 2 whole bankrupts and 1 lose a turn. So 3 of those 24 whole segments give you 0. Plus, there's actually 2 of those tiny bankrupt segments beside the 5,000. 2 of those little 70-second slivers there. And if you add those 2 fractions using a calculator or other methods, you get 11 out of 72 chance of getting nothing. So lose a turn or bankrupt. So I'm going to let you guys fill in the details there. And then once you have all the probabilities, you can just find the expected value by doing 200 times 1/24 plus 250 times 1 out of 24, and all the way up using all the outcomes. So it's a bit of a lengthy calculation, not really a difficult calculation. Like, we can all use our calculators, but just be careful because there's a lot of things to add and multiply there. So at this point, I've kind of set the problem up. I'd like you guys to finish the distribution table and then calculate the expected value. When you're ready, you can unpause and we will see how you did. Here we go. All right, so I have my table there. I've got all the probabilities I showed you guys and all the ones that I didn't, kind of filled in the blanks. Just, what could be helpful for you guys is to just do a check. I've mentioned that before, but it's adding up all those probabilities. So I'm looking at the first column here, and I'm adding these up. I got 5, 8, 12, 13 out of 24 in that column. And then I've got another 4, another 8. So I've got 21 out of 24. And then adding these 2 guys, 12 out of 72 is 3 out of 24, 21 out of 24 plus 3 out of 24. It does work out to 1, whether you made these decimals and added, but it never hurts to check your probabilities when you make a distribution, make sure they add to 1. And then when I did all my calculations, you'll notice I did not include the 0 calculation because 0 times anything is 0. So I just left that blank there, didn't include that. I got $536.11. So somebody spinning the wheel in Wheel of Fortune can expect, if they guess one single letter and get it right, they can expect on average to make $536.11. I apologize for the rowdiness upstairs. It just is what it is with the kids being home. This is a good value for the producers as well, because they can know how much on average they can expect to be giving out a game. It's also good knowledge for the contestants. For example, if they think they know the puzzle and how to solve it, but they want to make more money, they can think, well, if I know there's two R's to finish off the puzzle, is it worth risking losing all my money or my turn to get that extra 2 times 536, a little over $1,000? Is it worth $1,000 to maybe lose and not get the puzzle? Or is it worth, if I have 5,000 already, is it worth locking it in and solving the puzzle? So this is very useful information to know. And you can do it for any Wheel of Fortune wheel. All right, the last game show we'll analyze is Deal or No Deal. Here is a current state of a game. So you can see that of all the briefcases that were present, and I believe 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, there's 13 original cases, and then the person picks one. And there's 25 left to kind of rule out. But so they've opened up a $10 case, a 200, a 500, a 1,000, 100,000, 750. So their briefcase that they own is definitely not one of those guys. It could be they could win $1, or they could win $1 million. So the banker is just saying, you know what, you can stop playing right now, and I'll just give you $55,000. That seems like a good deal. But what we can do is we can actually say, well, what if I play to the end? Each of these cases has an equal chance of being my case. What can I expect to win? If I play to the end and don't take any deals, and then we can compare that with the banker's offer and see if it's actually worth keeping. So I've given you guys some space here. I'm going to move my picture there, leave it there. So a couple things for you guys to notice to make your calculation easier. So one, for each of our outcomes here, the probability is 1 out of 20. Like there's 20 cases left. Each case is equally likely to be our case. So it is a uniform distribution using that terminology from last lesson, which can make your expected value calculation easy to do. And because there's one way to get $1 and one way to get $2. So you don't need to multiply 1 times 1, 1 times 2, 1 times 5. You can just find the average of all those cases and divide it by 20. So that is when you have a uniform distribution, the expected value calculation can be pretty easy to calculate, just an average. So I'm going to let you guys finish it off, and let's see what you guys get. You can pause the video now and try that. Unpause when you're ready. Here we go. So if you add up all the cases, divide by 20, you get $128,335.40. So it's really interesting. If we played to the end, if we took this scenario and played to the end over and over and over again, on average, we would expect to earn just over $128,000. If you compare that with the banker's offer of $55,000, it might be in our best interest to keep playing. It seems like we can make more money. With 20 cases left over, even if we open up a few more cases, and even if let's say we open 2 more cases and we see the $400,000 case and the $500,000 case, the average of what's left is still going to be fairly high, and the banker's offer is still going to be in the tens of thousands. Like it's not like you're going to lose a whole bunch of money by continuing to play right now. In this case, for part B, if you would personally take the deal at this point, I think most people would keep playing, even because the expected value is a lot more than the banker's offer. And there's not really a crazy big risk in keeping playing at this point. We can be sure that the next offer, it might be less if we open up some expensive cases, but it's not going to be, only a few dollars. We still can walk away winning in the tens of thousands. So for part B, your answers can definitely vary for sure. But in general, I think most people would keep playing at this point. So that's it for today, guys. If you would like to keep working on the practice that you got last lesson, that'd be fine. But today was just to apply our knowledge of expected value in one particular way with analyzing game shows. Expected value can be very useful in analyzing lotteries, like roll up the rim competitions at Tim Hortons. It's extremely useful stuff. So I hope you enjoyed that. Hope you have a great rest of the day, and we'll see you guys soon.